So yeah, many thanks for the introduction. It's both a pleasure and an honor to be here. And you've heard and seen already a lot in the past week. And today, for the next 40 minutes, I'd like to take you on a little journey into the field of epidemiology, in particular spatial epidemiology. So today I will talk about geospatial modeling. And what is that? The story begins in 1854, where in London there's a cholera outbreak going on. And the belief of the day was that cholera was spread by miasma. Miasma is this bad, evil air going around. And whenever they saw there were terrible clouds in the sky, they were trying to hide from this bad air. And according to 1854, there was the best prevention mechanism from catching the disease. However, a doctor called John Snow started mapping all the cases on the map of London that he had. And so the red points here, as you can see, as what gave rise to today's field of spatial epidemiology. And after having mapped all the cases, John Snow also made plots of how distribution of water from different water providers looked like in London. And he overlaid those two maps. And guess what? He performed the first known in history process of inference in the field of epidemiology. And it turned out that the infection was spreading around the Broad Street in London, and the source of it was nothing else than a water pump. This is quite a prominent and historical moment for many, most of the people in my field, because we're still going through the same process with every disease nearly, except for our tools look slightly different. And the rest of the talk is dedicated to today's tool. So for the next 40 minutes, we're going to play the Jon Snow of today. So how does it look like? We normally work with some outcome data, which we observe, which we obtain via some tools such as surveys or satellite imagery or self-reporting of disease cases. And we use observational models. I will come back to this later, what observational models are really frequent and widely used in spatial epidemiology. The crucial part is that all of those models have one thing in common. They are defined by a linear predictor, which consists out of two components. And the first component in the linear predictor helps us understand associations with various factors, which we think are contributing to the disease. And the second part describes the so-called spatial random effect. And the spatial random effect in our applications is commonly modeled via the Gaussian process. So what are the three common scenarios that we face? There's three types of spatial data: aerial, geostatistical, and point pattern. The aerial data, also called lattice, is this data collected in an aggregated manner over space. So here you can see the map of United States, and we collected the data of vaccination rates per county. So each geospatial location in the county gets attributed exactly same value. The models which are widely used for aerial data rely on the borrowing strength mechanism. Basically, we're trying to model each region based on the values in its neighbors. Mathematically speaking, we use multivariate normal distributions with zero mean and precision matrix Q. And depending on specific form of the precision matrix, we define one or the other model of aerial data. Here's a list of the models which we use in practice. First of all is, of course, the independent random effect at each location, sometimes useful, but rarely. most likely that there is, for types of scenarios that we studied, there is some spatial correlation, and there are three common ways to describe it, such as conditional autoregressive model, where, so in all the slides, the matrix D is the diagonal, where each entry on the diagonal is the number of neighbors of each area. For those who work with graphs, both matrix D and A might be very reminiscent of what you normally deal with as well. So matrix A is the adjacency matrix, which reflects in a binary format who is neighbors with who. EGAR is the intrinsic conditional autoregressive model, and BYM is this model attempting to disentangle marginal variation coming both from independent variation in each area and variation coming from the spatial dependence. The second type of data is geostatistical. In this case, we collect the data in fixed locations in space. Think, for example, hospitals and weather observation stations. So those points are not random, they are fixed. We collect data there, and then the task is to predict or to construct this continuous surface over the entire space. So we want to make predictions at unobserved locations. And the mathematical tool to do it is, again, by Gaussian processes, where in this case we use kernels, which help us work with continuous processes. So the process of prediction of the values at unobserved location is called kriging. And I forgot to mention the task of prediction in the case of aerial modeling is termed small area estimation. The third type of spatial data is called point pattern. Visually, it might look very similar to the previous one, but there is one drastic difference. Both the number of the points here and the locations of the points themselves are random. So here we observe the spatial distribution of malaria cases reported in the country of Swaziland, and the points correspond to specific cases, so to the households where the cases were recorded. Mathematical tool to model point pattern data is point processes. There is a group of them. The most common one probably is the so-called log-Gaussian Cox process. The likelihoods look slightly more involved than for the other two spatial scenarios. However, as you can see in the bottom line, it still all boils down to the same expression, to the linear predictor, x times beta plus f, where x is our covariates and f is the spatial random effect. So in the nutshell, all those three very different spatial problems all have the same bottleneck, and this is the Gaussian process. And what is the long-term goal? What do we want to be able to do in reality? We want to be able to map diseases at scale. What is the scale? For example, we would like to be able to map diseases in sub-Saharan Africa at 5 by 5 square kilometer resolution. So you might think 5 kilometers is actually a very large distance. It's like between one village and another. However, if you consider such large surface that you would like to cover, 5 by 5 kilometer is very fine resolution. For some applications, also finer resolutions are of interest, such as 250 meters. So for 5 by 5 square kilometer resolution, to cover sub-Saharan Africa, we would require a couple of million points. And we're talking here just about the space, forget the time. So if we would like to take time into account, of course, the problem scales up. So how would we like to approach this problem? Now, it's very important. We do not want to develop necessarily new inference mechanisms, but we would like to use all the advances which exist in the area of probabilistic programming languages. So as an epidemiologist, as a modeler, I would like to pick my favorite language, and I would like to be able to translate my mathematical formulation of the problem into this language and rely on the inference which is happening behind the hood. So all I want to be able to do is to specify prior and likelihood, and let's call it press the inference button. What is very important for us? So as said, the problems are very large, and we cannot afford to rerun them many times. So the computation time is of essence. It does not have to be instant. So we're not talking about airplane flying and taking decision within a fraction of minutes. No, we can afford something longer. However, we do not want to spend months just to perform calculations for one model. And of course, yeah, convergence diagnostics is of great importance. So before using any results and trying to report them to policymakers in the space of public health, we of course need to validate that the chains have converged. So we look at Gelman-Rubin diagnostic and so on. So effective sample size is of importance because it tells us how efficient is sampling. So as I mentioned, all the problems in this field boil down to calculating the linear predictor. So the random spatial random effect is expressed via the Gaussian process when we evaluate it on a spatial grid, which is fixed in space. It all becomes a multivariate Gaussian normal of quite a high dimension, though. So what we would like to achieve? We would like to substitute this very heavy calculation with something that's simpler, that is easier and faster to calculate, which has ideally high effective sample size, but that at inference behaves in the same way. What do we mean by the same way? Why do we use Gaussian processes at all? We want to capture spatial dependence and characterize uncertainty. And what is the idea here? So the idea is to substitute that term in the linear predictor expressed by the Gaussian process by the decoder of a variational autoencoder. And what is good about this approach? So the bottleneck of a variational autoencoder is this random variable with independent components. We train the variational autoencoder to minimize the distance between this bottleneck layer and IID normal. So in the end effect, what we would like to have is this generative process where we start with the IID normal variable, pass it through the decoder, and reconstruct something that looks very similar to our initial multivariate normal. So why it should work before we even start experiments, or what should be in theory good about it? So if we represent the Gaussian process, excuse me, I think I messed up a bit the left and right side, the second line. I'll explain now better how it should look like. So in both situations, we can start an implementation with drawing an IID, so a standard normal random variable. On the left side, which should be representing Gaussian process workflow, we can calculate the L matrix, which is the Cholesky factor of the full covariance matrix. And so we calculate our Gaussian process realization at finite number of locations as the product of the Cholesky factor and the random variable Zn. So, and the dimension of the matrix and of the vector here is n, which is the number of points that we're trying to model. On the right-hand side, we also start with a standard normal distribution to draw the variable. However, rather than performing a linear operation of multiplying by the Cholesky factor, we apply a deterministic transformation, which is the learned decoder of the variational autoencoder. So it's not linear, however, it is deterministic. So there's no parameters in it to infer. while on the left-hand side, every time we are generating the surrogate of the Gaussian process, it does involve parameters which are unknown, which do need to be inferred. And the second point is that the dimension d is also possibly smaller than the input dimension n. So already two gains we're making. So we're reducing the dimensionality and we're substituting something very large and correlated with something smaller and uncorrelated. This is how the whole workflow looks like. It is a two-step procedure where first we fix the spatial structure of interest. If we work with log Gaussian Cox process or just statistical data, then this is an artificial grid created in space, for example. Or if we're working with aerial data, the fixed spatial structure is represented by administrative boundaries, such as counties, countries, and so on. So having defined the fixed spatial structure, we begin to draw priors of the multivariate normal. We can draw an infinite number of them because this is not a real data which we observe, rather the priors which we are drawing. And all these priors then serve as the input data to the variational autoencoder. Then the variational autoencoder is trained on these draws. And that was the first step. And the second step is actually the inference procedure, which means we open up the probabilistic programming language of the choice, implement the model, and just make a tiny alteration there, where instead of the implementation of the Gaussian process, we plug this train decoder working with the IID random variables. Here's a couple of examples how it looks in reality. So this, of course, is not any real-life spatial data. This is just an experiment in one dimension on a Gaussian process with RBF kernel. And the grid here is 400 equally spaced points on the unit interval. What you can see is what VAE has learned. So the VAE priors, let's call them, the mean looks very similar to just a straight line around 0, and it does show some range of uncertainty. Also, you can see thin green lines which represent the individual draws. How does this new prior perform for inference? Again, we start with a prior, which does not know much about our data. And as we are adding the number of points, then the uncertainty shrinks around the areas where we do have data, and uncertainty is wider where we do not have data. And that is exactly the behavior that we would expect from a Gaussian process in our applications. The method works also on irregular grids, so no need for the grid to be regular. Next step is to test it, of course, in 2 dimensions, because that is what we want to build up. The top row here shows ground truth with some added noise at the top left corner. And then again, as we progressively add more and more number of points, we see that the precision of the estimation increases, the top row, and the bottom row shows the amount of uncertainty. So the lighter the color, the less uncertainty there is in the estimate. So the bottom row progresses from dark to light, meaning that, again, it behaves similarly to how we would expect Gaussian process to behave. The more the data, the less uncertainty in the estimates. The previous 2 examples were building up towards those models of continuous surfaces in space, but what about the small area estimation? So when we get COVID, for example, cases reported over certain countries, such as UK, we don't get precise household locations. What we get is aggregated numbers. So this is an experiment also demonstrating that technique on a simulation working with aerial data. So how about some real life examples? Scottish lip cancer is not actually a real life example. Well, it was some time long, really long time ago. By now, this is just a benchmark data set. This is the MNIST of spatial epidemiology, if you want. And what is the model that is normally used? We model the number of cancer cases in 56 counties of Scotland. We're given the expected number of cases and also a covariate which characterizes exposure to sun acquired via activities performed in agriculture, fishing, or forestry. So the assumption here being made is that the more time you spend in the sun, the higher is your risk of cancer. And that is the model. What we want to look at is the linear predictor. As always, it consists out of two parts, the fixed effects and spatial random effects. The spatial random effect here chosen is the BYM prior, which is a Bezag-York Morley model. Consists out of two parts. Phi 1 characterizes the individual variation, independent variation in each county, and Phi 2 characterizes variation due to the fact of being neighbors with some other counties. Now, as I said, we need to run through a two-step procedure. First, we need to forget absolutely about the inference model, what the likelihood is. All we want is to generate draws from the priors. So in this case, from the BYM prior. We generate a lot of draws and then we perform inference. And here on the left-hand side, what you can see are the estimates for each county, both the point estimate in the middle, as well as the amount uncertainty obtained by the original model and by the model using the VAE prior trained on BYM prior. I must be honest here, it's not always that we observe this perfect alignment of the uncertainty levels. There are parts in the training where we can account for it. So this is a bit of manual tuning that you need to do, or come up with a smarter way, smarter loss to match the amount of uncertainty present in the initial prior. This is a case where it worked out of the box just perfectly. Visually, so of course, quantitatively, we could characterize the difference, but visually, I bet you can hardly tell which one is which. Here are the characteristics of those two inference runs. So first of all, the effective sample size, the larger the better. You can see it's not 10 times larger, but quite significantly. Also, the runtime, on the contrary, is way more than 10 times faster for the new model. This is how the results look like. So we start with some observed data. I would like to model it using two models. In the middle is a BYM, a regional model, and on the right is this new trained model. Again, visually, I bet you probably can't tell them apart. I spent really a lot of time trying. I found a couple of areas where they do differ slightly. It takes some time and skill and experience. Here's more of a realistic example, closer to our days. This data is coming from Zimbabwe, and it measures HIV prevalence. So HIV prevalence is modeled as the number of positive cases in every area, given the all number of tests which were performed in this area. Again, on the left is the original data, and the middle and on the right are the two models. So the original model in the middle and the new proposed model on the right. And this is to give you an idea, for example, so of the effective sample size. We can see that the original prior car wanders around, while the VAE car much sooner finds its trajectory. Also, the autocorrelations in the car model decay really slowly, while the VAE car pretty soon, all the correlations are nearly negligible, autocorrelations are nearly negligible within the samples. However, also we can see that the uncertainty is not exactly matched, and that's displayed on the leftmost plot. As said, this requires a manual process. So for the first case, we were really lucky. For the second case, a bit less so. So if we wanted to use this model in real life, we would need to go back and tune a bit the likelihood, which we use as reconstruction loss while training the VAE. And we could also match the variance better. This is the last example. Very close to probably everyone's heart because it's COVID. I think it was year 2021. And here the data consisted out of observed number of COVID cases per each LTLA level in the UK. And roughly there were 336 of them. So think 350. That's more or less the dimension at which this method has been used now. Still very far from a couple of million that we want to be able to do for Africa, but already not too bad. So what have we gained? Because yes, of course, when you look at the results of what the learned priors can achieve, they look very promising. And of course, everyone wants higher effective sample size. Everyone wants faster computation time, but this all comes at a cost, and the cost is that we need to spend time before running our model using MCMC to train the variational autoencoder. So we need to really understand what are the benefits to keep us motivated. And yeah, the motivation is that we were able to substitute a complicated, large, hard to compute correlated structure with an uncorrelated one. We also reduced dimensionality. So we started with dimensionality n, and then use the bottleneck layer to reduce it to dimensionality d, where I have not mentioned that d is a deliberate number that we choose. Also, we achieved higher effective sample size as wanted. We load the computation time, amazing, which will allow us to iterate through new modeling variations much faster. Another additional benefit of this method is that the amount and both quantity and quality of the data used to train the VAE here is unlimited, because the data that we use to train it is not any data that we need to go to the field and collect. This is data which is available for free. Well, if you consider computer simulations free. We can always define a noiseless prior, and we can draw as many of them. Also, there is no need to store them. If we would like to use 1 million prior draws to train the VAE, that is absolutely possible, because we do not need to draw them all in advance and store as a data set. No, we just draw one batch at a time. Of course, not all the issues with this method have been solved. It does look quite promising, but still there's a lot to do before we can go and map Africa at 5 by 5 square kilometer resolution. As I mentioned, loss is a very big question. Manual tuning works, but ideally you would like to take the human out of the loop, especially if this human is an epidemiologist, not computer scientist. So having smarter losses would be really helpful. And there is nothing wrong about trying to encode other distributions, not just multivariate Gaussian normals. This is this is all for today. Please, yes, stay in touch if you have any questions, because I don't think we have any time now.
Okay, thanks. So questions from the audience?
Hi, nice work. So I'm wondering that is the method, or have you observed any method that can incorporate any like features of the geological location into the modeling? And also have another question is that what if the data is very sparse, unbalanced. That's they can be very sparse in some location and very dense in some other location. How you deal with that?
Sorry, what's the first question? If we accounted for what?
So that for example, in the COVID data, you only have the cases now in the data, but maybe you can receive some how to say features about this geological location. So maybe incorporate those data into the modeling. You will get a better prediction and inference.
Okay, so the first question, yes, absolutely. Normally, what we want to do in real life, the whole purpose of building these models is trying to find factors which are associated with the outcome. This work is more the proof of concept. So we are developing new models and mechanism of faster inference. So when the next pandemic hits, we can literally just press the button and estimate, because so what you're talking about, yeah, is the purpose to estimate the strength of associations with other factors. This particular example was not doing it because, yeah, its purpose was to prove the concept. But yes, for example, the first example about lip cancer and fishery, that example did have a predictor equivariate. And the second question, I already forgot.
So that maybe you have a very sparse data in some locations.
Yeah. Okay. So I think here answer is easy. It's, you know, it's not about down to the model. It's like garbage in, garbage out. If your data is bad, no amount of effort in your modeling can fix that. But of course, due to using models which characterize uncertainty, this will be reflected in the estimates. So in the areas where data is present, the uncertainty will be lower, and away from the data in the areas where there is nothing, we will see that we have produced some estimates, but we do not trust them very much.
Thank you.
Other questions?
There's Yasin. What's that?
Hi. So yeah, continuing from what you're talking about, you use the example of yeah, Scottish lip cancer, and yeah, you mentioned that particular example was dependent on the factors of yeah, exposure to sun, but you also mentioned that in that example there was less manual yeah, intervention
yeah.
required.
Tuning of the VAE training, yeah.
Right. I'm not. So are these things related? Do you reckon that maybe maybe having some factors that could influence that the distribution could be based on?
Yeah, I think, okay, I understood your question. Thank you. The answer is no, because the process of training is completely disentangled from the inference model. So the predictor, the exposure to sun, only came into question when we started assessing the effect of exposure to sun. So the first step of this procedure does not see any real data. All it sees are the draws from the prior. So there's no way for predictors and the VAE training to interfere. That's, again, a good part. So once we have trained the VAE on a spatial structure, it does not matter for what application we will use it. Then, you know, how the pre-trained neural networks exist and computer vision and so on, many other fields. This is the same idea. You can pre-train a neural network for any geographical structure, and then someone can just go and download it and use it for politics, climatology, wars.
So it's just based on the spatial weight matrices.
Yeah, yeah. So we encode those spatial correlations.
Okay, I give a short question. My question is that, like, from the look, I would expect that I want to have a non-stationary GP, but you presented everything with stationary GPs, and probably the VAE learns the stationary GP. And so two questions are basically, one question would be, are non-stationary GPs used in epidemiology or not? And the other question is, how do you account for learning the, say, like the hyperparameters of the GP in your VAE model?
Okay, good question. Understood. Thank you. So first, yes, generally non-stationary kernels, of course, are used. They're much more rare. But the reasons they're not used is practicalities. Yeah, because it's much easier to use stationary kernels. Having said that, if there was an easy way, again, for practitioners to implement that, and there was guidelines and training mechanism, I think that would help very much the spread of non-stationary GPs. Second, learning the hyperparameters. Very good question. So depending on how the priors are trained, the information about hyperparameters might be lost. However, there are hacks, for example, to learn the marginal variance. So one way to pass the data is to say, talking above RBF, so our kernel looks like sigma squared times exponent of something. So if I draw my GP using this kernel, then I completely lose in the end effect information both about length scale and marginal variance. However, if the draws which I draw are only based on the exponential part, so I kind of draw I train the standardized Gaussian process, so I leave the marginal variance for later, and then in the inference model within my PPL, I write down sigma squared times this decoder, then I still retain the ability to learn about the marginal variance. Yeah, thank you for the question.
Thanks for the talk. Similar, I think, but maybe it was not clear to me that how you actually learn the GP prior, because in the VAE, I mean, you're trying to approximate the posterior by placing the standard normal, but here I didn't get exactly how you learn the GP prior of.
So, okay, let's be completely honest. This method is not learning functional spaces. It is learning vector spaces because, so the first step of the procedure is to fix the spatial structure, right? So if I say I work on a unit interval and I fix 400 points, every time what I generate is not a function, it is realization of a function. So in complete honesty, this particular method, there is a variation of this method though, which is targeting functional representations, but that is a separate story. So what it learns, so the VAE does not have notion of the draws coming from a certain distribution. It purely sees data. So it's not being told at any point in any form that what it targets is a Gaussian distribution. No, it just gets draws. It's like data, you know? So I show you MNIST images all the time, or I show you closed images all the time. Just go do your dimensionality reduction VAE and try to find a representation of this data. So it does not have any notion. That's why what I concluded with is that chances are very high that other distributions rather than just a multivariate normal can be learned using this method.
Thanks.
Other questions? No. Okay. Okay, I think we can thank the speaker.
Thank you all very much.
Thanks.